Okay, young people, this is Miss Stover again. I'm going to be finishing up the ice tables examples that you have. Those of you that weren't here in class today, I'm going to try and present the beginning part of it in another video, but right now I'm going to be taking off where we left off in class today. So here's the first problem, and it's a little uglier than the one that we did in class, but suppose you have 3.00 moles of H2 and 6.00 moles of F2, and they're mixed in a 3.00 liter flask. Assuming that the Kc is 1.15 times 10 to the second, what are the equilibrium concentrations of each species? So we're assuming that we're not at equilibrium yet. So how do we approach this? Well, the first step is always to balance the chemical equation. So we have H2 and F2, and that yields 2HF gas. So we have to always make sure we have a balanced equation, first step. Second step, we have to write the equilibrium expression. So looking at the balanced equation, we can see that the equilibrium expression is going to be HF squared divided by H2 times F2, and that's exactly what it is. Then we have to calculate Q, but in this case it is not necessary because we are only given reactants. We don't have any HF, so we don't have to worry about Q because we know that we have not reached equilibrium. We haven't even started the reaction. So we don't have to do step 3. So step 4 is the ice table step. So we have a balanced equation. Let's set up the ice table. So ice table, ice stands for initial. So the initial concentration of the H2 is 1. Why? 3 divided by 3 is 1. The initial concentration of the F2 is 2 because 6 divided by 3 is 2. The initial concentration of HF is nothing because we don't have any of that. We now know because we have no product, the only thing that we can do is form product. So what's going to happen? Well, we're going to lose X amount of H2 and X amount of F2. Why do I say X? Well, because they're both stoichiometrically 1. But we're going to gain how much HF? Well, because it's got a 2 in front of the HF, we're going to gain 2X. So the change, we're going to subtract X from both the reactants, and we're going to add 2X to the product. You see, it's pretty easy. You're using stoichiometric ratios. So what is the equilibrium concentration according to what we have on our table? Well, the equilibrium concentration is 1 minus X, 2 minus X, and 2X now. So now we have to solve for X. So how do we do that? Well, we get the equilibrium expression out, and we use the constant that we were given. So we know that 1.15 times 10 to the second is equal to 2X squared over 1.00 minus X times 2.00 minus X. Well, this is the problem. We're going to have a little issue going on here, and I'm going to get rid of my face so you can see the next slide. You must rearrange it and use the quadratic equation to solve this because you've got this quadratic piece on the back end, that 1.00 minus X and 2.00 minus X, and you're going to have a 2X squared. You've got this issue. So we can't just solve this by squaring because we don't have everything squared like we did in the last problem. So we solve, and this is what we get. We get 111x squared minus 345x plus 230 is equal to 0. So getting everything on one side to be able to solve for the quadratic. The quadratic equation is x is equal to negative b plus or minus b squared minus 4ac over 2a. Remember, a, b, c. Okay, so those are the numbers that we're going to use. When we plug those numbers in, we get two potential answers because of the plus or minus. The two potential answers of x are 2.14 or 0.968. Now, this is the issue. One of them cannot make sense. You can't have two answers here. So which one cannot make sense? Well, let me tell you. 2.14 cannot make sense. Why? Because you're only given 1 and 2 concentrations of H2 and F2. You cannot get rid of more than you have. So this one cannot make sense. This is the answer that we're going with. And you're always going to do that. You're always going to assume the answer that makes the most sense. You can't have negative answers either. So because you can't have negative concentrations. So we're going to use the 0.968. So if we use the 0.968, the next step is to find the equilibrium concentrations. Well, what was it? The first one for H2 was 1 minus X. So 1 minus X gives us 0.032. For F2, it was 2 minus X. So we get 1.032 when we take 2 minus X. And then for HF, it was 2 times X. So we get 1.936 for that one. Now, we always have a double check here. We want to check answers by putting it back in the equilibrium expression and making sure that we actually get the constant that we said we were supposed to have. So here we go. Putting it back in the equilibrium expression, this is what we get. And you can see when we solve, we get 1.14 times 10 to the second, which is really, really close to 1.15 times 10 to the second. So for all intents and purposes, that's a good thing. All right, so next problem. I think we might get a little uglier, actually a little nicer way to do this. So you can see the ugly way involves the quadratic equation. If you don't have the quadratic equation that needs to be used, you can use squares and things if you can, but you know, if you have to use the quadratic equation. So make sure you have that. So gaseous NaCl decomposes to form gaseous NO and Cl2. At 35 degrees Celsius, the equilibrium constant is 6.1 times 10 to the negative fifth. Notice that number is very, very small. In an experiment where 1 mole of NaCl is placed in a 2-liter flask, what are the equilibrium concentrations? So we see 1 mole in a 2-liter flask. Everybody got that so far? All right, so what's the first step? First step is always to balance the equation. There it is. 1 NaCl goes to 2 NO and plus Cl2. So the equation is now balanced. Step 2, what is the equilibrium expression? Well, clearly the equilibrium expression is going to be NO squared times Cl2 divided by the concentration of NaCl squared. Yes, it is. That's exactly what we should get. Okay, now we have to evaluate Q. But again, it's not necessary. We were not given any products, so it is not necessary to evaluate Q because we only have the reactant NaCl. So we don't have to worry about anything else. So next, set up the ice table. Notice how I write the equation up here at the top, and I'm going to put my numbers right below that for my ice table so that I'm keeping track of what I'm talking about. So my initial concentrations, I had no products, so NO and Cl2 are going to be 0. What's my concentration for NaCl? Well, remember, I had 1 divided by 2, so I'm going to have a half molarity, 0.5 molar, actually 0.500 or 0.500, whatever number of significant figures. It really doesn't matter at this point. We'll get that back later. What's the change? Well, I only have a choice to lose NaCl and gain NO and Cl2. So how much do I lose? I lose 2x, I gain 2x, and I gain x. Why? Because it's stoichiometrically viable. The 2, and the x come from the stoichiometry. So the 2 here, and the 2 here, and the 1 here comes from the fact that I have 2 moles here, 2 moles here, and 1 mole here. The minus is because I have to lose reactant. The plus is because I have to form product. If I were going the other way, I would subtract product and gain reactant, depending on where Q is. In this case, we only have reactants. We've got to go toward products. So what's my equilibrium expression now? 0.5 minus 2x, and then 2x and x. So now I put it into the expression and solve for x. So there's my expression. Now this is the deal though. Since K is very small, the change in reactants will be very small. So we're going to assume the change is 0. What do I mean by that? Well, remember the reactants are right here. What I'm going to do is I'm going to assume that this change right here is 0. So I'm just going to square the 0.5. I'm going to cancel this out and make it 0. 0.5 minus 0 is 0.5. 0.5 squared. That's exactly what I'm going to do. When K is very small, I can do that. I can make that assumption because K being very small means not a lot of product is going to be made. So, and it comes out to be a pretty okay assumption, and we'll see that in a minute because remember there's a double check later. Okay, so when we do that, we see what we get for the expression here. So 4x cubed is divided by 0.5, and we get that 1.0 times 10 to the negative second is our answer for x. All right, so now we've solved for x. We've got to find the equilibrium concentrations. Remember, we subtracted 2x from 0.5. So what do we get? 0.5 minus 2x gives me 0.48 because of the tininess of that. Okay, so let me go back for just a second. So 1.0 times 10 to the negative second is 0.01. 0.01 times 2 is 0.02. 0.5 minus 0.02 gives me 0.48. Okay, so what did I gain? I gained 0.02 in NO and 0.01 in Cl2. So how do I double check that? Let's check the answers by putting it in. Here we go. We get the number 1.7 times 10 to the negative fifth. And considering it's times 10 to the negative fifth, that's pretty close to 1.6 times 10 to the negative fifth, so that's an okay assumption. So when we have very small k's, you can do this. So you can see a couple ways to solve it. If it's simple as squaring, both sides are squared, and we can just take the square root, you do that. If it's not that simple and you have to use the quadratic, use the quadratic. If we have a very small k, we can assume that the change is small and get rid of the x on the denominator, the bottom, by making that assumption. So I hope this helps you in trying to solve these problems. Thanks.